Hey guys, so we're starting chapter 7. There's only 3 sections in here. This first section is on sequences. What I'm going to do is try not to read you guys everything because I know you guys can read and do the notes yourself there. So I'm going to just point out the most important things, okay? So what we're doing is a sequence. So we have a collection of numbers that have a pattern, okay? So you can either have your pattern in your numbers, so like 1, 3, 6, 10, 15, or you can have it in different shape patterns that show different things. So here we got squares down here, and we get 1, 4, 9, 16, 25, okay? Now, each number in the sequence is called a term. So you'll see me say like term 1 or term 2, okay? Now, if you see a dot, dot, dot at the very end, it means it goes on forever. It's what we call an infinite sequence. So what we're going to do to start out this section is that we're going to look at different sequences and see if we can find the pattern, okay? Now, you got to look in different cases. You've done something in secondary 1 with arithmetic and geometric sequence, but I know that's been a while. And we've done some stuff last year in secondary 3 towards the end of the year with series and stuff like that. So let's keep in mind out for this pattern. So for A, we have 1, 1, 2, 3, 5, 8, 13, so on and so on. Because it's 1, 1, and then 2, I automatically know, hey, it's not going to be arithmetic or geometric. And I'll go over those terms again if those sound unfamiliar. But what I do see is a pattern here. I might not look at the beginning, but I see here this is 0, but watch this. If I go 2, isn't it 1 plus 1 is 2? 3 is 1 plus 2 is 3. 5, 2 plus 3 is 5. 8, 3 plus 5 is 8. So let me go back. If we're adding the first 2 terms in front of the term, that makes sense because this would be 0. 0 plus 1 is 1. Okay, so what's happening is this pattern is actually what we call a Fibonacci sequence. Fibonacci. So in these problems, it also wants us to state the following 2 terms. So knowing that we're adding the 2 terms to get the next one. 21 plus 34 is 55. Then we're going to go one more term out. 34 plus 55 is 89. And we're done. All right. B, what do I see here? Well, usually I like to start out with addition to see if there's any connection. So let's try addition. 1 plus 2 is 3. 3 plus 3 is 6. 6 plus 4 is 10. 10 plus 5 is 15. And I do see that there's a pattern. It's like I'm adding 1 more to each term we go up. So the next one we're going to add 6. We get 21. Next one we'll add 7 and we'll get 28. All right, C probably is the one that I want you guys to get used to being able to recognize, because 1, 4, 9, 16, 25. What do all these numbers have in common? They're perfect squares. We have 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. So we're just going up 1 more and we're squaring it. So 6 squared would be 36 and 7 squared would be 49. All right, let's check D. -7 to -4 is adding 3. Well, let's see if that continues. -4 plus 3 is -1. -1 plus 3 is 2. 2 plus 3 is 5. So I'm going to add 3 each time. That's the pattern here. So after 8 would be 11, and then 14. The next page is some other patterns we're going to recognize, and I want you guys to really look at how I'm finding these out. Okay. So we have 64, 32, 16, 8, so on and so on. But if we look and we look at addition and subtraction, like I did on the other page starting, we would be subtracting 32 to get to 32. But if we subtract 32 from 32, we would get 0, not 16. So it's definitely not adding or subtracting. But what are we doing here? 64 to 32, well, that's half. 32 to 16 is half again. Half, half, half. So what are we doing here? We're multiplying by 1/2. You can say dividing by 2, but when we start writing equations for these patterns, you'll want to use multiplication. So my next number would be 1 and then 1/2. Now, one of the ways that we could have tested multiplication is to test that division, saying the second term divided by the first term. Does that equal the third term divided by the second term? And it does, it's half. So it's one term divided by the one before it when testing for multiplication. All right, let's look at F. So this is definitely not division. It kind of looks weird. But let's see for this. Let's see, 37. How do we get to 32? Subtract 5. 32 to 27, we subtract 5. And we realize this is all subtract 5. So let's continue and subtract 5. We get 7 and then 2. All right, 81, 54, 36, 24, and 16. Well, let's try the adding and subtracting first. So 81 to 54 would be subtracting 27. Well, let's see. 54 minus 27, that doesn't give me 36. So it's definitely not subtraction. So we gotta try the multiplication step. Remember, as an E, we can try that because it doesn't look like a nice multiplication. Is that we take a number and we divide it by the term in front of it. So I'm gonna go 54 divided by 81. Does that equal 36 divided by 54? And it does. They equal each other, but what they actually reduce down to is 2/3. And we find that this pattern, to get to the next term, you're multiplying by 2/3. So if we continue doing that, the next value would be 32/3. And then the next one would be 64/9. All right, H. H is one of the ones where we don't really actually have an adding and subtracting, but you can see other patterns. The first thing I want you to notice is that it's alternating. So positive, negative, so alternating. And then I want you to see the numerator, I notice right now goes up by 1 each time. 1, 2, 3, 4, 5, 6, 7, 8. So that looks good. What about the bottom? The bottom, the denominator also goes up by 1. The only difference is it started with 2. So I automatically know, since this is negative, the next one's going to be positive. My numerator is going to be 5, and my denominator is going to be 6. The next term would be a negative, and the numerator is going to be 6, and the denominator is going to be 7. All right, we have alternating again, but if you look at this, I like looking at these two right here because I can recognize that, well, wait, 15 times 3 is 45. And 2 times 2 is 4. So did that work the whole way through? Can I say -5 times 3 halves? Does that equal 15 halves? Well, it equals a -15 halves. So what do I have to do? I have to make the 3 halves negative. So that's why it becomes alternating. So in this pattern for I, we're multiplying by -3 halves. So our next two terms are going to be 135 over 8 and -405 over 16. Okay. Again, I'm going to summarize this down below. When we have patterns, most of the time, there are two formulas that we can create to help us find these patterns, or not find them, but find a term in the pattern. We have a recursive formula and an explicit formula. Excuse me. The difference is that the recursive uses our pattern and uses a term before. So just like the ones before, I found the pattern and I kept doing it to the final term to find the next one. Now, of course, with recursive, if I asked you to find the 100th term, you would need the 99th term to find that 100th. Well, to find the 99th, you need the 98th. That is the problem with recursive, is it uses the term before the one you want. So if it's a large value, you might not want to. Like on here for E, if I wanted to know the, let's see, this is 6, 7, 8. If I wanted to know the 10th term, it might not be that bad to like just keep multiplying by half until I go to the 10th term. But if I asked you to find the 100th, the last thing you want to do is write out 100 terms. That is where the explicit formula comes in. So the explicit formula is an actual equation that we create that allows you to find any term at any place. Okay. Now, some things that I want you to be aware of. N is the term. Okay. Nth term, the first term, second term, third term. Okay. The other way that we indicate that we're talking about the value of a term would be A to the N. Okay. So when I see A subset 5, I'm talking about the number of the 5th term. Okay, so the other thing we want to think of is our ends will always start with 1. So those are our counting numbers, our natural numbers. All right, so let's see what we can do here. Another way that we can see a written sequence is that they'll actually put the function here and then the ending value, or infinity. Don't forget, infinity means it goes on forever. And then the starting value down below. We'll see more of those as we go along. So find the first 4 terms of each sequence. So in this case, we have our function. We're going to start with n equals 1. So what we do is we plug in that value of 1 into our equation. The next one, we would plug in 2 to the equation. 3. See, it wants us to do the 4th term, right? This one's a little bit easier. This one should look familiar from years past, right? So we get, what is this, 8, and then 5, 2, -1. So our first 4 terms in the sequence are 8, 5, 2, and -1. Now it's a little bit more simple, but here you got to look at the complication of this. N, okay, first of all, this tells us that our first term is 8. So we're going to start out with 8 as the first term. The second term, what we do is we have A subset 2 minus 1 times 1/2 to the 2 minus 2. Okay. Well, 2 minus 2 is 0. Anything to the 0 is 1. A to the 2 minus 1 here, the subset, would be A subset 1. Well, what was our A subset 1? It was 8. So this is saying 8 times 1/2 to the 0. Well, that would equal 8. So far our pattern goes 8, 8. Let's try the next one. So we would say 3 minus 1 for that subset times 1/2 of 3 minus 2. All right, A subset 3 minus 1, so 3 minus 1 is 2. So we're going to take the value of A subset 2, which we got was 8. And we're going to multiply 1/2 to the first. Well, what value does that give us? That gives us 4. So far, 8, 8, 4. Let's do the last one because we want 4 terms, right? So A with 4 minus 1, or subset, I should say. 1/2, 4 minus 2. All right, so 4 minus 1 is 3. So we're looking at the term for 3, the value of the term 3. So that would be 4 times, and this is going to be 1/2 squared. 1/2 squared is 1/4. 1/4 times 4 is 1. Awesome. So now, what would happen if we were to graph the sequence in part A? So in other words, we would be graphing the point, well, at 1 we're at 8, at 2 we're at 5, at 3 we're at 2, and at 4 we're at -1. I'm not going to graph these right now, guys, but the truth is when we put these points in, it becomes a line, or it looks like a linear equation. And that makes sense, right? Because our function was linear. All right, I'm not going to worry about the graph right now. Let's worry about plugging in. This goes on forever, but we're finding the first 4 terms. So the first one, I would have -1, plug in my 1 for n, so 1 plus 1, 1 over 1 plus 1. When I calculate this out, I get 1/2. Okay, let's do the next one. 2 plus 1, 2 over 2 plus 1. Well, that gives us a -2/3. -1, 3 plus 1, 3 over 3 plus 1. What does that give us? That gives us a 3/4. Do you guys notice that this is a pattern on the other side? So let's break this down and see what this tells us. 4 plus 1. So we're using the n value a lot, right? The number term. What was that? -4/5. How did we get the alternating there? Do you guys realize we got the alternating from this -1 and these exponents? Excuse me. Because an even would make it a positive and an odd would make it a negative. So if we were ever to make up the equation from a pattern, we need to remember that to do alternating, we have a -1 out front to an exponent. All right, let's look at the next one down here. We're going to start with 1. So 5 over 3, 1 minus 1. Well, that gives us 1, or 5, sorry. 5 over 3, we're on the second term, so 2 minus 1, 5/3. And 5 over 3 third minus 1, that gives us 5 over 9. And our last one, 4 minus 1, that's 5 over 27. Okay, so that's how, when we have equations, we can state our terms of our sequence by plugging in that n value. All right, let's get into the definition of arithmetic and geometric. So most sequences, there are two types, there's arithmetic and geometric. Arithmetic sequences are which each pair of consecutive terms differ by a fixed amount, so adding or subtracting. Where geometric is about a multiple, so we're multiplying. I know multiplying and division go hand in hand, but when we're making up the equation, we want to think multiplication. Okay. All right, so what we're going to do is here's some vocabulary. Arithmetic sequence have a common difference. This is what the constant is between each term, where the geometric sequence is a common ratio because of what we're multiplying by. Excuse me. Like I said before, the ratio is a term divided by the one before it. And as you can see, it's indicated by n, meaning the term y, and n minus 1, the term before it. Okay. Same thing, so this helps us find our difference, and it puts it in a general form to find that difference or ratio, okay? So what we're gonna do now is identify from example 1, if it's arithmetic, geometric, or neither. So if it doesn't have a common difference or a common ratio, it's neither. So A, remember that was a Fibonacci sequence. What it was doing was adding the first two terms in front of it together. So adding the first two terms wasn't always adding the same thing, correct? So that means it is neither. B, what were we doing? We were adding 2 and then 3 and then 4 and then 5. So are we adding the same thing? No, we're not. So it's neither. C, remember we were squaring everything. Were we squaring by the same number? No, we weren't. So it's neither. And D, what was our pattern? It was adding 3 each time. So that means it is arithmetic because we were adding 3. E, we were multiplying by 1/2, so that means it's geometric. F, we were subtracting 5, so it's arithmetic. G, we were multiplying by 2/3, so it's geometric. H, we didn't have a multiplying or dividing, we just saw a certain pattern in it, so it is neither. But for I, we were multiplying by a -3/2. So it's geometric. Hopefully that sounded familiar. All right, example 5. Determine if the following sequences are arithmetic, geometric, or neither. If arithmetic, find the common difference. If geometric, find the common ratio. Okay, so first of all, if we were to look at this pattern by plugging in, right? And plug in 1, we get 3. Plug in 2, we get 5. Plug in 3, we get 7. What are we doing every time, guys? We are adding 2, so it is arithmetic. By the way, do you guys see that 2 comes from the slope? That will come up later. All right, and B, well, if you remember, we did this pattern on the other page. It was 1/2, -2/3, and 3/4. Are we multiplying by the same thing? No, we're not. So this is neither. And you can test that out by checking that A subset 2 minus A subset 1 does not equal a subset 3 minus a subset 2. If the difference between the terms were the same, then we would have a common difference. Same thing as if you were testing out the ratio, we would say a subset 2 all over a subset 1. We find out that it does not equal a subset 3 divided by a subset 2. C, let's look at these numbers. Remember it was 5 5/3, 5/9, 5/27. Okay, right away I see 5 is just on top, right? So to keep 5 on top, we would be multiplying by 1. And on the bottom, what happens here? We go from 1 to 3 to 9 to 27. What are we multiplying by? We are multiplying by 3. So since we are multiplying by a common ratio, we are geometric. Ta-da. Okay, formulas. So a couple things when we talk about making the equation the explicit formula. We have to remember that arithmetic is going to look like this. Any term can be evaluated by taking the first term plus n minus 1 times the common difference. Same thing for a geometric sequence. Any term can be found by the first term times the common ratio to the n minus 1. So that is what we're going to do. We are going to look at these patterns, find out if it's geometric or arithmetic, and then plug in whatever common value we have. So on A here, what happens? Well, as you can see, guys, we're adding 5 each time. Adding 5 means it is arithmetic. So what do we need when it comes to an arithmetic explicit formula? Well, we need a subset 1. So a subset 1 is that first term, which in this case is -6. And our common difference is 5. So now what we're going to do is plug it into our explicit formula. So a subset n equals our first term plus, and usually we like the d out in front, right? Because usually we put that value out. So plus 5 times n minus 1. And we're done. Okay, B, what's happening here? First of all, it's alternating. So I know I'm multiplying by a negative. Well, 5 to 10 to 20 to 40, what am I multiplying by? I'm multiplying by 2. And on the bottom, I go 1, 3, 9, 27. So I'm multiplying by 3. So my common ratio is -2/3. And I need my first term in this. My first term is -5. So I got to look at my geometric. So my equation is a subset n equals -5 times -2/3 to the n minus 1. Done. All right, so that's nice, right? But of course, we're going to get into some other things that we need to look at what's given to us and what we need to find. So the first term of an arithmetic sequence, so remember, it's going to be the a subset n equals a subset 1 plus n minus 1 times d. Okay, the first term, so let's see what it gives us. A subset n, a subset 1 is 15. A subset 10 is -12. What we need to find is the common difference. All right, what I want to point out that is here, a subset 10 equaling the value of 12 means that n is 10. That is the biggest thing you watch out for. Because now when I plug it in, a subset n is a value. Our value is going to be -12 equals the first term, which is 15, plus n minus 1. What was n again? N was 10 minus 1 times d. And you know that you're doing okay because I only see one variable, and that's what I want to find, right? So then we have to do some algebra. So negative 12 equals 15 plus 9d. Subtract 15 from both sides, we get negative 27 equals 9d. So our common difference is minus 3 or negative 3. Okay. All right. What are some other questions that can be put on us? Well, the first term of the arithmetic sequence. Okay, let's look at this. So we're looking at a subset n equals a subset 1 plus n minus 1 times d. First term, so a subset 1 equals negative 12. The common difference is 5, so d equals 5. Which term of the sequence? So we're finding n, and a subset n equals 58. So we're finding the term, the value of the term is 58. So let's plug in. We have 58 equals negative 12 plus, I'm going to put d in front because I like having my coefficients in front. N is what we're trying to find. And are we having one variable now? Is it the one we want? Yes, it is, so we can go forward. So 58, I'm going to add 12, so I get 70 equals 5 times n minus 1. I do not have to distribute, because right there, how do you get rid of a multiplying 5? We can divide it. So what is 70? 70, looks like the notes were misplaced. 70 divided by 5 is 12? No. 14? Was n minus 1. Add 1 to both sides, we get n is 15. So it's the 15th term. There we go. All right, next question. This is another one. Find the value. So we're finding a subset 13, which means n is 13. Arithmetic, so let's say we're going a subset n equals a subset 1 plus n minus 1 times d. Okay, in the arithmetic sequence, when a subset 10 equals negative 14 and a subset 30 equals negative 54. All right, what can we do with this? Well, what we're going to do is actually plug both of these in, and then we have a system that we can solve for, okay? So, a subset 10, which is negative 14, equals a subset 1 plus, that's the 10th term, minus 1 times d. A subset 30, that's negative 54, equals a subset 1 plus 30 minus 1 is d. And now look, guys, this is a system, right? So I actually can subtract these straight down and come out with d, right? So negative 14 minus a negative 54 is a positive 40. Now, if you want, guys, you could say this is 9 minus 29. right? Which gives us a negative 20d. So negative 2 equals d. All right. So what we now need to do is plug in. We are trying to find a subset 13. Okay, what we need is the first term, right? How could we find the first term? Can't we find the first term just by plugging in d to one of these equations? So 9 times negative 2 is negative 18. Negative 14 equals a subset 1 times negative 18. So a subset 1 equals 4. So now let's plug that in. It is 13 minus 1 times negative 2. I know I'd rather have that in front because it looks better. Now when we calculate that all out, you find that a subset 13 equals negative 20. All right, let's look for a new question here, right? The fifth term in a geometric. Okay, let's write down geometric because we've been used to so many arithmetic. So it's a subset 1 times r to the n minus 1. Okay, the fifth term, so a subset 5 is 4/5. The common ratio is 2/3. We're finding the first term and going to write the explicit. Okay, so right here, this also tells me n is 5, right? So let's plug it in. So we get 4/5 equals a subset 1 is what we're trying to find. Oops. Our ratio is 2/3. And then we're doing it to the n is 5 minus 1. All right, 5 minus 1 is 4. We can do 2/3 to the 4th in our calculator. So we get 4/5 equals, and when we do that in our calculator, you get 16/81 times a subset 1. How do you get rid of a fraction? We divide, or not divide, multiply by the reciprocal. So I'm going to multiply each side by 81/16. 81/16. What happens is we get that a subset 1 equals 81/20. So when we write it back in the explicit, we get a subset n equals 81/20 times 2/3 to the n minus 1. Perfect. And now we are done. Okay, so the next section would be on series. Make sure you're labeling all the given information, figuring out what you need to find. Also, make sure you have the right explicit formula.